Okay, so let us look at some examples involving the principle of mathematical induction, right? And that we know that this principle of mathematical induction is a method of proof to prove something is true for an infinite number of cases. And the way it's going to work is that we'll be given a proposition or a hypothesis, and we're going to be told that we want to show that this holds true for some infinite set of integers, right? And that process becomes to show that the basis case is true. So you're going to show that my first integer value for which the proposition is hypothesized to be true, that first value, when input into the proposition, does work. Then we're going to assume true for a general case. Then we're going to consider the subsequent case. And we're going to use that inductive hypothesis where we assume true for the general case. We're going to use that inductive hypothesis to determine if the original proposition will still hold true. And if that proposition does hold true for the first case, and when we have our inductive hypothesis, it necessarily follows that the subsequent case must also be true. Then, by the principle of mathematical induction, our proposition is proven to be true for all cases. So let's look at an example here. Prove using mathematical induction that for a positive integer n, and we have our information here. Now, how else could we write the information about having a positive integer? All right, we could write the notation like this to indicate a positive integer. So our basis step, right, our initial case is to consider our first positive integer, which is 1. Right? If we look at the left-hand side, right, if we look at the left-hand side of our proposition, the left-hand side is going to be the cosine of theta plus I sine of theta, right? Because there's just cosine of theta plus I sine of theta raised to the first power, right? And the right-hand side is also going to be the cosine of 1 times theta plus I sine of 1 times theta, right? So we have our left-hand side is cosine plus I sine theta to the first power. The right-hand side is cosine of theta plus I sine theta. Therefore, our first statement is true, right? Our first case is true, and that is because the left-hand side equals the right-hand side when n equals 1. Okay. Then our inductive hypothesis. Our next step is that we're going to assume true for n equals k. Right? So in other words, we're going to assume that the cosine of theta plus I sine of theta to the nth power, or in this case, kth power, because n is going to be k, so to the kth power, will be equal to the cosine of k theta plus I sine of k theta, for k being some positive integer. And we're going to assume that this is true, right? We have to assume that we have this true. Okay, so next we're going to consider when n is equal to k plus 1. So therefore, we're going to consider the cosine of theta plus I sine of theta raised to the k plus 1 power. So that means that our left-hand side has to be equal to the cosine of theta plus I sine of theta raised to the kth power times the cosine of theta Let's write that a little bit more neatly. Plus I sine of theta, right? Using properties of exponents. Okay. Now, we are going to use our inductive hypothesis. We're going to use our inductive hypothesis and say, hey, you know what? We're assuming that this is equal to that. So that means we're going to then consider this as cosine of k theta plus I sine of k theta. All of that multiplied by this cosine of theta plus I sine of theta. Okay. Now, if we go ahead and multiply, we've got the cosine of k theta times the cosine of theta plus I cosine of k theta times the sine of theta plus I sine of k theta times the cosine of theta, and then plus I squared sine of k theta sine of theta, if I go through and do my distribution. Okay. Now, rearranging these terms just a little bit, that's going to give me, let's see here, let's change the color so we can see it a little bit better. So if I rearrange these terms, that's going to give me cosine of k theta cosine of theta minus sine of k theta sine of theta plus I times the sine of k theta cosine of theta. I'm just trying to line these up. And then plus the cosine of k theta sine of theta. All right. Well, using my properties for trigonometry and my trigonometric identities, then I have that this is the cosine of k theta plus theta plus I sine of k theta plus theta, which is really then just the cosine of theta times k plus 1 plus I sine of, and if I wanted to pull out in this direction, I could say k plus 1 theta, right? Which way I factor to the left or factor to the right, doesn't matter. Right? So, what does this mean? This means we are true for n equals k plus 1. Right? So, our final step then becomes our conclusion. Our final step then becomes our conclusion. We can say, because, right, P of 1 is true, and when P of k is assumed to be true, it follows that P of k plus 1 is also true by the principle of mathematical induction. Our proposition, our P sub n, is true for all positive integers n. And that's our work for mathematical induction, right? So if we look to this idea, I can come over, let's make this just a touch smaller where we can see everything all at once. And we say, to prove by mathematical induction that for a positive integer n, this proposition holds where I squared is -1. Then we follow our basis step. We make our inductive hypothesis. We consider our k plus 1th case. We use our inductive hypothesis to show that the k plus 1th case will also be true when the inductive hypothesis is true. And then we make our final conclusion statement that because we're true for our first case, and when our inductive hypothesis is true, it follows that the subsequent case is also true. Then by mathematical induction, my statement, my proposition, must be true for all of the integer values that I was considering. And in this case, all positive integers, this infinite set of integers. And this particular statement will always be true. Okay? So hopefully that makes a little bit more sense for mathematical induction. This was an example using our trigonometric identities. Thank you for your time.